Talk quickly about converting things to and casting and static casts. Let's review static casts. The reason for reviewing static casts is you have to use static casts for project one. You get a void star and it's got to become a function pointer. Well, actually, it's an array of function pointers. The pointer of a function pointer. Okay, so I realize this is probably covered in 312, where everything in the entire C standard was covered. Since C++ is a superset of C, and everybody comes out of 312 with a mastery of every detail of C++ 2017, then you really ought to know all of the C stuff except for nested functions. I really look forward to teaching 312 and finally actually learning how far it's possible to stretch everybody in one semester. And there is a limit to how much you can teach in one class in a semester. And if you try to teach more than that, there's like so how much content you put in the class, it's got like kind of a linear relationship at first, right? More content, more stuff people know at the end. But if you go too high, it starts to actually get worse as you start to increasingly just say gibberish that nobody understands. So the trick is to find that ideal point. And part of the other trouble is people that are pulling off an A performance in the class might have that point be, here, I'll use an emphasis color, that even people that can't see colors can see. You know, it might be up here. And and then people that are probably going to fail are, maybe down there. And so you have to pick some point between these three and try to aim for pulling everybody up as high as you can. Because you don't want to cut the class off here, because then these people are going to feel like they didn't get their money's worth. But if you pull it up here, then you've got like one person that's been stretched as far as they can and learned lots of stuff, and everybody else has had an inferior experience and could have learned more. So anyway, that's part of it. So I always picture 312 going up here, but the reality is it goes somewhere rather shorter than that. And it's not anybody's fault. I mean, this is just how human learning works, right? This is why in the Matrix they plug the thing into your brain and then you learn everything. They wouldn't have had to set that up if people just kind of learned everything immediately, right?
And in a semester, you're only getting like 40, 45 1-hour lectures.
Right, right, yeah. Yeah, so, yeah. Oh yeah, so anyway, but back to static casting. So, suppose we have something here. Suppose we have int and a, and it's 5. Okay, we can say print out percent sign d and print out a. Okay, piece of cake. Make this a void name, since we can say that in the modern C standard. Okay, so everything's good there. So we go ahead and make that static cast. Yeah, okay, so fine. Now let's make a float. B equals A. Okay, and we'll print that one out too. F is a float. Okay. Now, the reason I picked float, double is maybe more commonly used as the base floating point type these days in C and C++. It's like coffee. A single espresso shot is about 6 grams of coffee, and if you want it to taste reasonably good, you don't want to put it in this size cup or it'll taste like coffee kind of water. If you're going to make this size cup, you need like a double shot around 14 grams, or maybe even a triple up around 21. And so the actual number of singles that are made at, say, Hot Shots or Dutch Brothers or somewhere like that in Lewiston is probably about 0. Everybody uses a double. So the same thing applies here. People usually use the 64-bit type. Now, I have a particular reason for using float, and it's not just because I've been typing float in GPU programming, because GPUs actually still use floats. It's because it's the same size as an integer, they're both 32 bits. Okay, so we can say that this is one of those. So let's go ahead and build this. Okay, so we've got 5, and we've got 5.000000. Good. Okay, so everything was okay here. Now, let's go ahead and cast this. Okay, we'll go ahead and build it again, and everything is fine. So we asked it to take this number, and it's going to be a float, and the compiler is happy to do this in a manner that everybody can approve of. Okay, let's make a thing called C, and this is a float pointer, and so it points to a float. And so then we'll say that C is the address of B, and it'll say printf %f the thing that C points to. So C points to something, it points to the value of B there, so we should get 5 again. Okay, great. We have become experts at printing out 5. So let's go ahead and say instead this is going to be the address of A. Okay, now we've got a warning. Initialization from incompatible pointer type. Let's run it. That is not 5. Here's what's gone on. We had this A. This is the address of an integer. Oh, let's get rid of the warning. We'll use a static cast when we get rid of the warning. Okay. Float star. There, no warning. Still doesn't work. Okay. It makes good sense that it doesn't work. Let's try the other way too. Okay, we'll make int star d, this is the pointer to an integer, equals, as an int pointer, the address of b. So it's like d for an integer, b. Okay, oh, thing d points to, sorry. Not b, d. Did I do that right? We got an int pointer d, and we're printing out the thing that d points to. And the thing that d points to is actually b here.
Address.
Well, it has the address of b in it. Okay, that is also not 5.
That's a great number.
Okay, so here's what's going on here. This is not a very good use of a static cast, but it illustrates what a static cast does pretty well. When you take a static cast up there where we say float A, we're telling the compiler that we got this thing, it's not a float, but we're about to store it in a float. And it's okay with that, and it'll actually convert it to 5.0000 for us. This is the standard promotion behavior in C. If you take something and you said, it said something like this, float D equals A divided by 1.0. You get a float, say 2.0. Okay. We need a name here, E. Okay. Sign F for float, and we'll print out E. Okay. So we expect we're going to get 2.5, right?
Should.
Yeah. And we will. Okay, 2.5. Okay. Now suppose we go ahead and say instead of 2.0, we just said 2. Ooh, look at that.
Integer division.
Integer division. Okay, suppose we say 2.5f. This will actually be slightly more efficient. 2. Oh, wait, 2?
Yeah.
Oh, it's a 2.5.
No.
Okay. The reason it's more efficient, so when you say 2.0, the default type for a floating point these days is a double. And if you wanted it to be an actual float, you just say an F at the end of it. We've been doing this a lot in GPU programming since most of the time we actually want a float to go send to the GPU. You can do that. You don't have to do it, whatever. Okay, so that's the standard behavior here. So if we take A up here, it's going to have that standard behavior happen to it. With promotion, it's not a direct straight across. We just took this set of 32 bits and put them into this other spot for 32 bits. What we're actually doing is making a conversion. Now, a little bit of under the hood CS250 type stuff. The x86 processor has different registers for floating point compared to integer. And back in the old days, you could buy an x86 processor like an 8086, and it would not have floating point capability.
You'd have to get a
Separate
chassis.
Right. Now, floating point can be simulated by a number of integer operations. And so it wasn't exactly true that you couldn't perform floating point arithmetic. It was just that it had to be synthesized by doing various integer operations, which is slower. So if you had a motherboard that was sufficiently weighty and expensive, it would have a socket in it, and you could buy an x87 floating point processor with its own registers and put it in your motherboard, and it would start working, and floating point would get faster. So if you had a favorite game and it depended heavily on floating point, it would run better. If you didn't have anything that depended heavily on floating point, and a lot of people bought them without having anything that depended heavily on floating point, then your computer would act exactly the same. I guess maybe it uses a tiny bit more power. I think my dad added one and had the same result. Anyway, later the x87 floating point unit got integrated into the actual processor, but it still has its own registers. So when you say this up here, the compiler has to put instructions in to take an integer value, convert it to a floating point that is the same value, like numerical value, and put it into a different register. So it's actually doing a bunch of work. And it'll do that automatically. Now, when we say this down here, we're sort of bypassing this work in an unusual way here. So we got float C, which is actually 8 bytes here, 64 bits, because it's a memory address. And it's the memory address of a floating point number in computer's memory, not in a register, just regular memory. So we're going to say that the number that we store for this address, remember an address isn't really that special. An address is just a 64-bit unsigned number. That's it. So we're going to take the address of this variable A, that's actually the address of an integer, and we're going to pretend it's the address of a float so that the compiler doesn't complain, otherwise it throws a warning. And we're going to put it into C here, and so now we're saying, hey, at this point, C is the address of a float, but really, that spot in memory contains an integer. And so when we take that integer and look at it like it's a floating point number, we get something different. And then the same thing happens in reverse. So so the float there is a single precision floating point format occupying 32 bits. And so the representation we're looking at for a float is something like this. It's probably exactly this, actually. Anyway, so we got a sign here, we got an exponent, which is 8 bits, and we got a fraction that's 23 bits. And so when we store a 5 as a float, we've got the 5 here as the fraction, and we've got some kind of exponent. And so when you take that whole set of bits here and pretend it's an integer, there's actually some 1s way over in this area. And since there's some 1s way over in this area, that's why we get a big number. When we go the other direction, the exponent's all zeros, the sign's all zeros, all this stuff is zeros. There's just a couple of 1s way down in the small part of the fraction here, which don't seem to be factoring in given that there's no exponent, and we're getting 0.00000 printed out. I would almost expect a very, very, very small number to come out, but that doesn't seem to be what's happening. So, and we're using it quite incorrectly. It may be that you have to have something in the exponent spot. Anyway, I haven't thought about single precision floating point for a long time because I haven't taught CS250 for a long time. Okay, it's been just as long for me as it has for you guys. Okay, so that's a static cast used kind of wrongly. Okay, let's use a static cast in a little bit more of a correct sense. Okay, I'm thinking of a good example here. Okay, suppose we have some sort of function, and this is a lousy example. Okay, here we go. We got a function that that works a lot like pthread create. Okay, so pthread create takes a start routine and it takes this arg up there, and then something happens with this arg. So we're going to make a function, and it can take an argument, and it can actually be a couple of different types. It's a little bit of a weird example, but we'll do it anyway. Okay, so this returns a void star, so a memory address, and it's called add, and it takes two parameters here as void stars. And maybe it'll take a type code. Okay, and we'll define a couple of types. So it could be either of these types. So we'll say if type is an int, okay, so then we have ints. So we'll say int star a. And so we want to add these two things together. So a is an int pointer, and b is an int pointer. But we also want to say the thing that these point to. So we'll add up the thing that each of these things points to. And that'll be our result. So that's our result. Okay. And if we're going to return the address of our result, then things are going to go badly for us, possibly. We'll just do it. And no, we won't just do it. We'll do this. We'll say that here we go. Instead of a void, we'll return an int, but it might actually be a float. No, let's not do that. That's silly. Well, we'll actually allocate. We'll do this like a normal person. I realize it's a little silly to call malloc on 4 bytes, but it'll be fine. Okay, so we want to make our res thing first. We'll say the thing res points to. So res, an int pointer res equals int pointer malloc size of int. Okay, that's done more correctly. I don't have any objection to this being done in a hacky way now. It's okay. Okay, so then we run the return as void star res. Okay, and so then the other option, type is a float. And it's going to be the same kind of thing, except that we're going to be using our x87 floating point unit, and all these are going to say float. Okay, there we go. Else, unsupported type. Oh, let me say what type they did. %sign D. There. Cool. Okay, and we'll return 0. If it wasn't needed, but okay. So now we've got a function add there. So we should be able to say something like this. Int, I need some new letters here. We'll go x, y. X equals 5, y equals 10. So we should be able to say now int star res equals add, and then we'll have the address of x, address of y, and the type. Okay, then we should be able to say printf result equals the thing that reset res points to. Okay, and it will free it because we want to be good today. Okay, so that will use this add function, and add up there can figure out what its types are. See what we forgot? Oh, implicit declarations of malloc and free. They're both in stdlib. It was actually nice enough to include that. And the fact is, it actually found it in build a program too. So we'll be good. Okay. So there we go. Result is 15. Okay, so you can use static casts in this kind of circumstance. In this little contrived example here, we don't know what the type of A is because this function actually supports more than one type. And then afterwards, we're going to have to figure out what type we're dealing with, and then we can make a cast to treat it as the appropriate type now that we know what that type is. Okay.
One thing about that's confusing. Down when you called your add function and you're handing it the address, you'd think it'd be actual, the hexadecimal address, not actually what's sitting there.
Yeah, it is. It's the address of X.
So wouldn't you be adding those two addresses and it would make something funky happen?
Well, no, because we said that this is the address, so it's got the address here. The void star is generic pointer, and so it's got the address here. So then down here we're saying, take this address, assume it's the address an integer, and then this star here is the one that actually does it. Take the thing that the address points to.
Okay.
So that's yeah, it's called dereferencing right there.
I've seen examples before. It's just I haven't used it a lot, so
Yeah,
that was confusing for a moment. I'm like, wait a minute, you're adding two addresses and this is working.
Yeah, no. If we here, I'll get the stars out for a moment. probably throw a warning.
Yeah.
Invalid operand, we can't add two end pointers? Well, but we could do this. Instead of saying that it's the address of an integer, we can say that it is a size key, because that's an unsigned 64-bit integer. Since we can cast these things. That's fine. There we go. That's the result.
It actually added the addresses.
Yeah. Yeah, we just tell it that instead of an address, now it's a size T.
That's weird, but it makes sense.
Yeah. Yeah. So the usual way to get tangled up in this stuff is just to miss some stars and ampersands and things.
Speaking of which, you missed one.
Did I?
It's the same star.
Oh, you're right. What's it do? Error, invalid type argument of unary star, have type integer. Here's why. So we took A. A is actually a 64-bit unsigned integer as an address there because it's a void star. So we took that address and we converted it to an integer. It actually doesn't fit. An integer is 32-bit, it's 64. But the compiler is being okay with this. It's taking the lowest 32 bits, so if there's anything that's just too big a number, it doesn't count. Then we're taking that and saying, okay, take this 32-bit piece of it and pretend it's an address, and go fetch what it points to. And it's like, you said it was an integer. It's not an address. It's not even big enough for an address. Yeah.
Interesting.
Yeah, it'll give you commentary a lot of times. The other thing is when you're using the static cast here, a lot of times it, the compiler's like, okay, they said the static cast this, they must know what they're doing. Okay, yeah, that works fine. Okay, so if you had, say, a function coming in as a void star, then you just have to cast it. Here's one other way to cast it. Let me change the way we cast it. Okay, so we'll do this one differently. Okay, so I'm going to take this and make a float VA, and this is going to be the value of A. And so we'll say that this is, take A, and we take the thing it points to, and we'll pretend it's a float star. Oh, here sorry, I forgot the intermediate. Okay, so this is a pointer to A equals, as a float star, A. Okay, do the same thing for B. Okay, and then down here, instead of putting all of this nonsense on this line, we just say PB and A. Okay, do the same thing. Let's verify that it works before I start saying it's fine when it's not. I guess we never actually ran that code. Anyway, come on. So we've got this PA and PB that are pointers to A, or pointer A and pointer B. And we've done our casting here so that it's already a float star. And so then down here, we don't have to have quite so many stars and parentheses on our line. You can use this trick on question 1 in a project if making a list of function pointers by static cast just turns out to be too many stars and ampersands to get right. And it very well might just be too many to get right on the same line. And so you can do an intermediate stage like that. That works fine. You might look at this and say, wait a minute. We're allocating an extra 16 bytes of memory, so this is going to be slower because we're using more memory. And that's true the way it's stated, but any optimizer worth its beans can figure out how to put this back in order. So in a practical sense, it's actually the same speed because those won't really exist. Okay, part of the art of making a fast and clearly readable program is to do stuff like this when it makes it more readable, but think about whether the optimizer is going to figure out what you just did. And if it looks like something the optimizer can figure out, like this is trivial, right? I mean, this is the same thing as this, which is that. So if you just took this and put it here, that would fix it. Trivial. And so if you got something trivial like that, the optimizer will almost certainly figure it out. And so we're not really making the code run any slower, we're just making it clearer.
Makes sense.
Yeah. If you really like optimizers, we don't have a class on optimizers. We don't have a class on compilers either, so that would be a prerequisite to a class on optimizers. I took a class on compilers, and then I took a graduate level class on compilers, but it already had the compiler content, and so I actually ended up doing like a special project on optimizers. I always liked optimizers a lot. Anyway.
230 is kind of like that, no? I think it was 230, the one that I took with Charles. It was like just optimizing files and all those.
250? Yeah, but it doesn't really cover compilation techniques and how to build a compiler, intermediate representations and things like that. Yeah. That'd be a good 492, compilers. I like the class I took on compilers. We wrote a compiler. Okay, so that's that. So I'm hoping that's maybe helpful for the project. Maybe it's not. Okay, so we already did this stuff. This is actually last time's notes. We talked about the utilities and whatnot, but I wanted to actually show you how to put a module into the kernel. And so we did some demos with modprobe and whatnot. Haven't talked a lot about symbols. I think maybe we should make a module and then get back to this stuff when we can see one. Okay, so I think I have one set up on this computer in Kmod. I just copy, well, I'll copy the blink.c to software. Okay, oh, there's a difficulty that occurs at this point in the class for reasons that are not particularly good. I can't use sudo to put a module into the kernel in a directory that's been mounted for my software using SSHFS. And so I end up with, this one gets a little bit out of sync. I also don't want to put the module on a software. Because normally that's what I've been doing, is building the program and running it on a software. Okay.
That's a good way to break a software, if you use kernel modules.
Okay, so I'll try to make sure all this stuff actually goes over there. Okay, there it goes. Okay, so blink.c. So this is a kernel module demo. It's been around for a long time. It's kind of a classic. If you go online, you can find an explanation of it since it's been around for like 15 years as a basic kernel module demo. Okay, let's explain what it does. So maybe we'll run it first. There's a make file in here that's actually set up correctly. So we should be able to build it. Okay, that should be built. So now we should be able to put it in. So if we look in here at everything called blink, we've got a blink.c, that's source code, piece of cake there. We've got a blink.o, that's an intermediate file. We've got a couple of other intermediate files that might or might not make immediate sense. But then finally, we've got this blink.ko. That's a kernel object, as opposed to a regular object. And it's been linked to the extent that it needs to be linked before it's actually put into the kernel. So now we should be able to say sudo install. Oh, whoa, we're on a software. Have it here? Yeah.
So you almost installed it on a software.
Yeah, I would have probably not actually ended up with it on there since I would hopefully, the passwords are different, so hopefully I would have noticed at that point. Maybe.
Well, that's
Okay,
good.
so we just built it on this machine right here. And so if they say everything is blinked there, we got that. So they say sudo install blink.ko, and then it should be in. Okay, here's what it does. The keyword LEDs are blinking now. Yay. Great. Yeah. And the fact is, when we take it out, so we'll say sudo rmod blink.ko, which again looks like you're deleting it. Okay, I'll just push enter while I'm holding this here.
Instantaneously turns
Stop. Now, the fact is, I think numblock is on. So if I push 7, oh no, it's off. It's possible to end up with them kind of in the wrong state with this program.
Yeah, if your numlock was on to begin with, so one was on, and then
Okay,
would it basically
we
toggle?
got numblock on, we just pushed it. Now they're blinking. So then we'll go ahead and rmmod. So now they're not. But you can see that numlock's on because when I push this 4 key, you can see it on the projector.
Uh-oh.
Now I push this again, numlock didn't change there, but you can see now it's the arrow because the cursor's moving over there. When we push it again, now we're back.
Well, at least it's easy to fix.
Yeah, it's easy to fix. It's just kind of funny that you can end up with the keyboard in the wrong state for a moment. Okay. So anyway, that's what it does. So And it's got, if you look at the blink.mod.c, it can drive you crazy trying to understand this file. We'll cover it a little bit more later. It's stuff that was produced in order to handle links and symbols and whatnot. Let's take a look in the blink file though. We'll go through and explain how this works, and that'll give you a feel for modules. So, first of all, we have a whole bunch of headers that we have to add that have Linux/whatever in them. These are Linux header files, so if you're curious, like Linux/console struct.h. This is for VC cons, but what is in Linux/console struct.h? You can just, I have another terminal around here. I'm not sure I have the kernel source code on this computer in front of me. I probably should, because that would give us the exact right version of that file. And but we'll just look at this one. It's going to be the same. That file hasn't probably changed in 10 years. Okay, so if we go in Linux source directory here, we go to include/Linux. We're going to end up with all these things. So with a file called console struct.c. Console struct.h. .h here too. Okay, so here is console struct.h. And so it includes a few other things. And then it's got an example VC data of a console that was scrolled 3 lines down, just as study that if you're ever doing anything really complicated with a console and you understand. I haven't studied that picture. And so then you can see these structures that have to do with the consoles. And there's a lot of stuff in these structures. Mostly just regular data, but you've also got a TTY port, which I think is the only thing we actually use from it. Okay, so these header files are real files. They're just under the include in Linux directory in your kernel source code. So then we got a module description, that's what it is. We got a module author, that's who wrote it. They've got a license. It's got the GNU public license. So this one does not taint the kernel. The GPL is an approved of license for inclusion in the Linux kernel. There's a fair number of them that won't. Any of the BSD licenses, for example, are fine. GPL in a nutshell says you can have the source code, do whatever you like, but if you modify it, you have to release or change it. This differs from the BSD license that says you can have it and do whatever you want, but please don't sue us. I think the GPL maybe says please don't sue us too somewhat. The GPL is long and lengthy and will take you a while to parse if you decide to read it. The BSD license probably won't. I think the MIT one's even shorter.
Something they had a lawyer help draw up.
Yeah, I mean, they're all drawn up by lawyers, but the lawyers had more work and charged more money on a GPL. Actually, they might not have. They may have been volunteers. They certainly had more work to do. Okay, so then we got globals. Now, the scope of a global. So globals are frowned upon more the bigger the scope is. So if you have some big program and it's 100,000 lines, a global is going to be frowned upon because it uses up that name for the entire program. With this one, the scope of this global is just this file. And this file is not even very long. So it's much less discouraged here. So we got a timer list and a TTY driver and a KV LAD status. I'll just show you these as we go down it. Okay, so we got a blink delay and we've got a code for all LEDs on, which is 7. These work the same way as the Unix permissions, where you'd say chmod and then give it a number like 4 or 7 or 5 or whatever. It works the same way. So each of the LEDs is a number. I don't remember off the top of my head what the values in number lock, caps lock, and scroll lock are, but one of them is 4, one's 2, one's 1. Okay, then we have a restore LEDs code that brings it back to the previous point, which apparently is FF. So then we get to the actual functions in here. And I want to bring you all the way down to the bottom to start. So we've got this module init and this module exit. So we can put the module into the kernel and take it back out. When we put it into the kernel module init, whatever function we specified here is called. Whenever module exit is, we have that one. So if you imagine the function prototype for module init, actually let's not imagine, let's go find it. Okay. Okay, so there's a bunch of places it's called, and there's a bunch of directories, and there's various defines and stuff like that. I want the actual place it's defined, and I think it's void. So I think doing that will probably find it. I really don't care about these directories. It's not in this directory. That'd be a good joke on me. You see, oh, that's possibly a confounding factor. So there's a bunch of different defines that can get done here. For example, in module.h, let's look at module.h. Okay, so this is part of the frustration in finding things in the kernel. There's this define here. So module init with parameter x is defined to be the same as _init call given a parameter of x. So the preprocessor is going to make that substitution. So if you want the example of, where's this parameter defined, the answer is nowhere. It's just a text substitution that happens for this init call. Well, it's a good rabbit trail, right? Init call. Okay. Not this file. Let's look for that everywhere. We'll save that R so we go refresh here. Okay. Oh, look at this. In init.h, init call a function. Yes.
Device init call.
Okay. So let's look for device init call. Okay. So this is probably done in a platform-dependent manner because you can see there's a bunch of platform-related stuff
Wait,
here.
it's redefined as define
Double
it.
underscore define init call with a function and a 6. Okay. So that's not in here.
No, it's not device, it's define.
Oh. Define?
Yes.
Yeah, they changed that.
Oh, you're right. I'm slightly dyslexic. Okay. So it looks like it can be just defined with more stuff on it, or we can have like early init call or all of this other stuff, but it might be that top one. Okay. There's a commentary on why it's needed. So define init call is defined as static init call type init call. That's probably defined somewhere else.
So what you're saying is finding anything in the Linux source code is following a huge amount of rabbit trails.
Yeah. So a compound function compound. I mean, it's used there. That's the only place it is in here. Okay, apparently that's not an okay pattern there. I think it got interpreted by the internal somewhere. Okay, R. Okay, that's the only place it's mentioned there, actually, oddly enough.
Oh, hey, look.
It's used in a few places. It may actually be put in when the whole thing is built. The build process is fairly complicated and involves defining a fair number of things that aren't actually really defined anywhere else. So I think at this point, instead of diving into the build process, we'll just give up for now. Okay, but if we finally got back to it, at some point, it's a function pointer. And so this one here, for example, expects something like this: static void _x. Oh, that's not it. Okay, static void _exit, which is probably defined somewhere to make something happen on this function. KLED is cleanup, which also returns void. So actually, it just returns a void. But this _exit is going to resolve to something somewhere. We can go down that rabbit trail, but we'll leave it for the moment. So there's a certain amount of this stuff where you just kind of got to trust that that's how it works. Okay, so inside KBLED's cleanup, all we actually do, so I print out this message. This appears on the kernel log. So if I go in here and I type the message, I can see this KBLED stuff, loading, finish scanning, etc. Unloading. So that unloading message there comes from right here. That's that message. So again, that's D message like that. Okay. So then we delete a timer, but I haven't shown you where we made it, and we restore the LEDs. But let's go ahead and take a look at the init one up here. So there's the loading. And then there's the console that we found, FG console. And so FG console, it's used a few times for FG console. So it comes from Linux tty.h. So TTY here stands for teletype. So back in the days when Unix came together, computers were expensive enough that people didn't generally have one. This is pre-DOS machine era. And so instead of having a computer that had expensive things like a microprocessor in it, you'd have a teletype, which connects via a phone line to the actual computer, which was housed somewhere else. And multiple people would use this computer via teletypes. So that's where this TTY thing came from. And if you look at /dev on Linux, to this day, we've got this TTY term. Now these days, you're generally not on a teletype. You're using an SSH session, like when we connect our software, where you have to be coming from a real computer, or you're using just like a virtual terminal, like this one, or something else. Okay, anyway. So tty.h has this symbol FG console. It is %X, and so FG console is 6. So it's finding which terminal you have. Now there's more than one on here. I've got several terminals open. The virtual terminals that you hit with Control Alt F1 or whatever probably count. And so you got some sort of ID for which terminal you're using. Okay. So then we go through this VC cons structure. And VC cons is in one of these ones right there, console struct.h. So what we've got is a VC cons right there. So let's take a look at VC cons. This won't be a bad reference. Okay. So include Linux and what is it? Struct something. Console struct. Okay, VC cons. Okay, so you can see we've got this external struct VC, so it's a type struct VC, and it's named VC cons, but it's actually an array of struct VCs, and the array that's the size of the array up there. So we just need to know what a struct VC is, and I think that's this long one. That's a VC data. Okay, there's a struct VC. So a struct VC is actually really pretty small. It's got a pointer in it. Oh, and it's got an actual one of these structures in it. You see, it's not a pointer. So this one's 8 bytes, and then I'm not sure quite how big a work struct is. But that's what the D member is. So if you look over here, we got this reference here to VC cons at position I.D. And it's a dot, not a reference. That's because this VC cons here is an array of struct VCs, not addresses of struct VCs, but actual struct VCs. So we've got this struct VC cons, and we're looking at .d. Now we're saying if not that one, then break. So the reason we would do that, we're searching through these struct VC conses one at a time, and eventually we're going to come to one that doesn't represent anything yet. Like we got this array here, and you saw that the size of the array there was max in our consoles right here. So I don't know what our max number of consoles is. Suppose it's like 256 or something like that. So some of these consoles are used and some of them aren't. This is probably why this is so small. We don't want to allocate a whole struct VC data unless we're actually using that console. So we have an array of references to it right here, and at some point we're going to hit the end. But instead of having some way to check how many we actually have, what we do is just go here until we're one too many, and then .d will be 0. That's where we get the logical not there. And so the reason it would be 0 is, see, this is a memory reference here. And so for the address of, you go through the addresses of various VC datas, and then when we get to an unused one, there's no memory address, it's just 0, and then we stop. So break will break us out of this loop right here. And down we go to there, and we print out finish scanning consoles. Okay, so then we print out this message here about these consoles that we have found. So that's the messages, the POET ATKN messages that these ones right here. So we found consoles 0 through 6, and we found that some of them have a teletype number and some of them don't. this is probably the virtual terminals up here. And oh, there, 63. That's our max number of consoles. So apparently if we push this button enough times, we probably cause a problem there. I'm gonna do that right now.
Oh, that might be interesting to see though.
It might be. I'm assuming it just won't make one. Here, we'll try this. Let's go ahead and make a bunch then.
The first one's 0, 63, so that would be 64 total consoles,
Yeah.
Oh yeah, yeah,
which would make sense, nice round number.
yeah. Okay. I want to print out all this stuff again.
I was wondering where that TTY stuff came from. I didn't know.
Okay.
Yeah.
Oh, we didn't get any more consoles. I have to think about that one. Oh, I think I know what happened. Let's pull back up. They probably, all the X server related ones, all the virtual window ones, are lumped together in one.
Yeah.
That makes it distinctly less interesting to try to use them all up. Okay. Anyway, so we run through all those ones, and so we got the TTYs there. Now, we got this my driver thing. So my driver, if we look for references to it, we find it's defined right up here. It's a reference to a struct TTY driver. And so the struct TTY driver, it's going to be in the include files there again. Still have those? Oh yeah, I have them right here. Okay, so the TTY driver is probably defined in TTY driver.h, considering there's a whole bunch of references in there. There we go. That's declaration, we're going to have it. The reason that this is oh, that's TTY operations. There we go, TTY driver right down there. Okay, so a struct TTY driver has some actual methods here. It's got this TTY operations. It's also got some information about the teletype driver. This is you should have some kind of device driver here inserted in the kernel. And it's got some information about it, but it's also got this TTY operations. So the TTY operations struct is full of function pointers. And so if you hadn't done project 1 or lab 1 yet, which you should have, and I should have graded it, and maybe I will this week. If you find a struct TTY operations being used somewhere, there'll be a whole bunch of places where these things are populated. Okay, so that's what a TTY operations is. Okay, so let's look at how it's used in our kernel module. Okay. So our driver here is going to be VC cons. So we're looking through the VC cons, we're looking at that. And it's an index FG console, which is a console we actually have, which is number 6. I remember printed out in dmessage. .d. And so the .d on the TTY driver, not TTY driver, spit out that and open up the console structure. So the VC cons, there's the D, it's the type VC data. And I think this thing up here is a VC data. So inside the VC data struct that's associated with it, we're going to look at the port.tty. So if you look over here, we got the struct TTY port right there, called port. Okay. I have to use quotation marks for that. And so that looks like it's in maybe tty.h. Okay. So there's port operations. That's not what we're after. That's a different thing. Struct TTY port right there. So we're in one of these. So the teletype port here. Okay, so we're following this line. So port.tty, and we're looking at driver. And so here we should have somewhere driver. Why am I not able to find this? The TTY struct has, oh, is it TTY struct? That would make a lot of sense if it was. Okay, I got caught in that whole thing. Okay, so the port.tty, we're the port. Oh, right. Okay. So we're the TTY port, and there's that. Okay. Okay, so I'm gonna have to go back to that port there. I lost my lost our sequence here at some point. Okay, so look back at this console struct. It's a TTY port is what this the type of this port is right there. So that's a struct TTY port dot TTY. Okay, so we need the TTY port. That's TTY struct. There's a lot of references to that in this file. Just a few. Go up to the top and the first reference to it. Okay, that's a TTY port. There it is, that one. Okay, so from that one, our struct TTY port, we're looking at TTY. Okay, there, that one, which is a struct TTY struct. Let's go up to the top here and just find it at the top. There's a TTY struct. Good. And so TTY struct has this number dev. Is that what we're after? No, we're after driver. That's not dev. There it is, which is a struct TTY driver. And so that's good because that's the type that my driver is a struct TTY driver reference. So we burrowed through all of these and we've got the right reference to our driver. Now the reason to have this my driver thing, sure we have VC cons and we can type this whole incantation every time if we wanted to. This is a simplification. Since we're going to be referring to this thing regularly, we don't want to have to say all this stuff again and again. Now we've got our driver there. And we're going to say what the TTY driver magic is. Okay, so that's a struct TTY driver. Maybe go up to the top and find the first reference. Maybe it's not defined in this file. That's entirely possible. Oh, it's in TTY driver.h. Of course. Yeah, it does. Oh, there, it's right there. Okay, so we've got a, there's what magic is. It's an int. Isn't that refreshing now after all of this? So magic. Magic number for this structure. Used to keep track of which drivers is a reference number for. Okay, so we go ahead and print out the magic number, and then we set up the blink timer. And this is going to seem refreshingly simple compared to the stuff we just went through. So init timer here initializes timers. So if we look at my timer is right here, and that's a struct timer list. And so struct timer list, you can actually have more than one timer there. So init timer, we go back over here and I'll look at init timer. Okay. There's a bunch of things that have init timer in there somewhere. I keep putting down R in there just to get rid of the extra stuff on there. So we got a timer.h, extern void init timer, enter timers, plural, and then we've got some defines there that define where this thing goes. I think I'll just explain what this one is instead of following that rabbit trail because it goes off through define world for a while before we come out on the other side. We could follow it, but I'll just tell you what it is. Okay, so my timer here, you can have kernel timers and they will go for a while and then they will expire. They don't beep or anything, they expire. That's what they do at the end. But when it expires, it will call a function for you. Here's the timer function, is my timer func. And so my timer here is an array of one item. At least that's how init timer is going to view it. We're going to give a reference to it, and there we go. Okay. So we got a my timer function. It's up above. We'll look at it later. We got some data for it, and this is data that's going to be handed to the function, and it's a reference to the variable kBLED status, which is the status of the ones. And then we set its expiration date, and it's set. We have a number of jiffies here plus the blink delay. So jiffies is the number of jiffies that has gone on so far. I think since the computer's been booted. And then blink delay is the number of jiffies we want to wait until this thing is going to go off again. The blink delay is set based on Hz, number of hertz here, and that divided by 5. You might be tempted to assume Hz is the frequency of your processor, but I don't think it is anymore. I think it was in the very early days. Okay, and a jiffy is not very long. What exactly a jiffy is actually changed a couple of times over the time that Linux has been around, but they've always been pretty short.
So we could change the blink delay and make it really, really short.
Yeah, we could.
And just have the strobe.
Yeah, just reduce blink delay. Yeah. So let me go ahead and add my timer to the current list of timers right here. And so once we do that, this function myTimerFunc, which is right up here, will be called in blink delay jiffies. Okay, and this one naturally turns the lights on and off. Okay, and then we actually use myDriver. So we're going to be using myDriver a lot. You can see part of the justification here. I mean, if we took this line here, this stuff, and stuck it into here, you know, man, what a mess. I mean, it's already a mess on this line, and it kind of was up there. And so you combine them together, and yeah, it's just not good. On this one, we have myDriver, and we're looking at ops and IOCTL, and then we got parentheses around it. So IOCTL is a function. And, so this is going to be a pointer to a function. You see the arrow there, so we dereferenced it. So IOCTL is a function. So from this parenthesis to this parenthesis, this is a function. And then this is the parameters for that function. So that's how the line deconstructs in a sense of what it does. So if we look at myDriver, we had this thing open a minute ago over in here. Okay, I think it was in tty_driver.h. There we go. So myDriver, and I think the next one was ops, if I remember right. Ops, yes. Okay, so where's ops? And oh, it keeps going, of course. And it keeps going past that. Okay, so ops there is a reference to a struct TTY operations. Now, I'm probably looking for a definition up above, not below. Right there, struct TTY operations. So in here, there should be the IOCTL function. There it is, IOCTL. Okay, IOCTL stands for input-output control, and it's become a more general thing than that. You see IOCTL is used for controlling devices all the time. It's sort of a generic catch-all for we're going to make the device do something or other, and you know, control it. And most of the devices are input-output devices, so most of the time the name actually makes a fair bit of sense. But it's kind of outgrown its original naming convention. So when you think of an IOCTL, just think of you're telling the device driver to do something. Maybe you should say asking the device driver to do something, because device drivers are funny things. In a GPU programming class, we frequently talked about how you might ask the device driver to do something, and it might actually do something completely different and then say that it did. And that's part of the point of device drivers. The device drivers have an interface on the operating system side where the operating system says, okay, go ahead and do this thing. And in the device driver, you know, suppose the piece of hardware works completely differently. Like the operating system is telling you to do something that was like something that we used to do in like 1974, and hardware doesn't do that anymore. The device driver will do something that it figures is probably close enough. That's part of the great thing about device drivers. Okay, anyway, so we call IOCTL here. So if you look at the parameters this takes a struct TTY struct, it takes an unsigned int, that's the command, and it takes an unsigned long, that's the argument, 64-bit unsigned value. So if you look over here at the parameters, you can see we've got commas here. for the right number of parameters. And so we've gone through our VC cons incantation again and got the port TTY out right there in order to give the IOCTL what it wants, which is a reference to the struct TTY struct. And then we've got this KD set LED, that's the command. This is defined up top here, KD set LED. I thought it was, maybe it's not. You know, here's where it's coming from, right here. KD.H for KD set LED. I say, well, what's KD set LED? Why not find out? Knowledge is power, right? Okay. Hey, isn't this great? So, this function here, this header file, is going to be short, actually. And all it does is include uapi/linux/kd.h. Okay. So if we go down a couple, let's just grep -r kd set LED, and then we'll grep for define. We'll see if we can figure out where it's at. Okay, there we go. So we sort of shortcutted the whole like rabbit hunt thing, and we we're just like, okay, search the entire source tree, find somewhere that we said KD set LED, and we said define, and that'll find where it's defined, right? And so there it is. That's the number. This is the command for set LED state. This is in hex, so 4B32. Okay, so that's given to this thing. Where are we at on this? Okay, so that's given to this thing, and then all lights on, which is a 0x7. This is the code for the number of lights. Okay, so I talked to the driver and did that. Now up here in my timer func, this is going to run whenever the timer expires. We get an unsigned long pointer, and so this is kind of like a void star, and so we're using it as an int star. So this is actually a pretty good demonstration of a cast, which is exactly what we were talking about yesterday. It's great. Okay, so down here we wanted to pass in KD LED status. KD LED status is actually global, and the funny thing is, it's actually a char. So KD LED status up here, this char, we're taking that and saying, okay, we'll get the address of it, then we'll say the address, which is a 64-bit integer, is an unsigned long, which is conveniently a 64-bit integer. Probably should have said size t, but this example is like 15 years old, and I'm not sure we even had size t yet. So then it comes up here, and it's still an unsigned long, a 64-bit unsigned integer. And we say, okay, PTR here is now the address of an integer. And so we're gonna store that here and say int p status. Same thing I did with the float stars, like PA and PV earlier. So p status is now a reference to KD LED status, except that we're pretending it's the address of an integer, not the address of a char. So then here, if p status is 7, then we change it to restore LEDs. Otherwise, we change it to 7, all LEDs on. And then we go ahead and call this IOCTL again with basically the same parameters, except we say p status for the status we want to set it to. So that's why it'll alternate between all LEDs on and restore LEDs. So back and forth we go. Okay, then the next bit of thing we have to do here is set when a timer is going to expire. That's the current number of jiffies that we're at right now since the machine started, plus the blink delay. And we go ahead and add it to the list of timers. So it automatically gets popped off the list when it expires. So it's like a microwave timer. You know, you set the microwave timer for something, when it expires, it beeps, and then it doesn't ever go again. So if you wanted to do something every minute, for example, and you wanted to use your microwave timer, what you'd have to do is set the timer for a minute. When it beeps, you do your thing, reset the timer. Now, it's actually going to happen at a frequency of a minute plus however long it took you to do all that stuff. And that's exactly what's happening here, because we're setting the blink delay here at the end after we've done all this stuff. And so we're at blink delay plus this amount of time. Now, this is not very much time. So it's pretty much at blink delay. If you're doing this in the physical world, doing something every minute, you can end up at a minute and 10 seconds or 20 seconds or however long it takes you. Okay. So then that's all set. So that's back on the list, so it can expire again. So that's why we delete the timer down here, get rid of it, and we call restore LEDs and turn them all off. And so that's the ending status of this thing. Restore LEDs looks like it should restore them to what they were before. It actually turns them off. So, yeah, I showed you that earlier. Okay. So that's an example, simple kernel module that involves interaction with a device driver. And so you might get the impression from this that kernel programming lines of code are more complicated on average than other programming lines of code. And in general, you're right. I mean, a kernel module has very few lines of code for the amount of time it takes you to scratch your head long enough to put them all together. And then the kernel itself, of course, has lots of lines of code, so now you can see why it takes so long to do the kernel. That's why Linus didn't just write the whole latest version in an afternoon and call it good. There's an awful lot of housekeeping that happens with moving from one structure to another. And so that's the point of project one in this whole talk about kernel C and pointers to this and that and function pointers and casting stuff. That's why we'll be going over that stuff for 3 weeks. You know, it's what you do in kernel programming a lot of times. But the bright side is, once you get good at kernel programming, then any kind of C references and dereferencing and whatnot is going to seem like it's kind of simple and straightforward. You know, if you decide to ride a bicycle home every day, whatever hill you ride up on the way home is an easy hill. And all the rest of the hills are harder hills. And so it doesn't matter what the size of that hill is, eventually that hill is easy. See, same way with this stuff. Okay, I think that's about all I've got to say about this Blink one. The next thing we're going to have to talk about on kernel modules before we can really start writing and making them do things is how to make entries in the /proc file system. And it's very similar. You just have structures and pointers to this, that, the other thing, and module entry points, and then it works. It won't be that bad. We'll do that on Tuesday. I'll post them in the lab pretty soon. I think the kernel one's due tomorrow. I've been thinking about what the next lab is, and I haven't quite decided yet. It could be making a simple modification on a kernel module so that you can build these things and put them into the kernel. I won't make you do something complicated with a kernel module because that'd just be mean. You can do that for project 2 later. Because with a project, you expect to spend a bunch of time on it. For the lab, you expect to be done in an hour, you know? So if it's one of those, it'll just be something simple like, you know, take that one up there and go actually build it, but only blink the numlock key or blink twice as fast or something like that. Yeah. Okay. Yeah, I guess that's it. See you all next time. Have a nice day.